Good evening, everyone. Thank you very much for coming up Sand Hill this cold and dark December night. Tonight will be our last public lecture for this year, and we are going to continue next year, typically the last Tuesday of the even month, so you can mark it already in your calendar. December is always an exception because we don't want to run into Christmas. I should also point out that in case of an emergency, you can use either the doors you came through when you came, or we have two more doors here. We are very lucky tonight to have Kelly Gaffney, who grew up in Seattle, and he told me that he likes salmon. He got his PhD in Berkeley and joined the faculty at SSRL in 2004. He will talk about an amazing machine we are very excited about at our lab right now. It is a machine which can make movies faster than you can imagine. Not 10,000 frames per second, not even 10 million, not 10 billion, but actually at a rate of 10 trillion frames per second. So please welcome Kelly Gaffney.
It's my pleasure to welcome all of you here to the Stanford Linear Accelerator Center, affectionately termed here SLAC. And as Uwe just mentioned, we are embarking on the building of a remarkable instrument. 2 years from now, we are going to be commissioning the world's first X-ray laser, and it's going to be able to enable a wide range of transformative experimental science. And tonight I'll be talking about one such experiment, the making of molecular movies, where this X-ray laser will be the integral part of that movie camera. Now, in very broad terms, the science that I am excited about is being able to watch a chemical reaction as it occurs in real time. But in addition to fundamental and broad scientific goals, as you'll see as I present my talk, these movies are also very much related to an important issue for society, which is the ability to have a renewable energy source, and a powerful one at that. So how can we harvest the photons from the sun to make electricity or fuel? And as you'll see is throughout my talk, I hope that you're able to observe how the LCLS and how it makes movies is very much tied to this scientific and technical problem. But before diving in deeply into those scientific issues, I want to start with a place where everyone in the room should be very comfortable, which is the power of images in shaping perception. So here we have a photograph, a rather old photograph of Abe Lincoln. And I'd like to bring two aspects of this picture to your attention. First off, look how messily he tied his bow tie here. And also he has a cowlick. Now obviously, Abe Lincoln isn't famous for his good looks. But the point I'm trying to make is the presence of photography, and now its ubiquity in our life, means that a president would never be photographed under these circumstances today. George Bush isn't going to be pictured in public with a messy bow tie. But obviously, as I mentioned, this is what he's not famous for. He's famous for his leadership and his oratory skills. His most famous speech, of course, being the Gettysburg Address, unlike a current president's oratory skills. And the interesting aspect is all of us, when we interact with Abe Lincoln as a historical figure, we're limited to photographs and the written word. Now, of course, the speech is not meant primarily to be read, but to be heard and to be witnessed in person. But because there were no cameras at the time that this speech was given, were limited to the words on paper. I'd like you to contrast that with another historical figure, which is Martin Luther King. Now, he lived much more recently, and as a consequence, not only do we have his words and pictures of him, but we also have the ability to see movies of his speeches. Almost to the day, 100 years after the Gettysburg Address, Martin Luther King delivered his I Have a Dream speech in Washington, D.C. And this we can now watch in real time. The main point I'd like you to notice is the emotional impact of a movie versus the written word is enormous. And it's my hope that a similar impact in the physical and life sciences will be achieved by moving from photographs and complex ideas of chemistry to actually making movies. Now, there are a lot of technical challenges to moving from photographs to movies, whether we're taking pictures of people or of molecules. And a similar transformation occurred in the 1800s with regard to movies. So the reason why in Abe Lincoln's time we weren't able to have a movie, here you see the oldest photograph from 1826 that survived, is this photograph required an 8-hour exposure. So unless you're interested in watching the grass grow, it's very difficult to make a movie under these circumstances. This idea of exposure time is very critical to the making of movies, and this idea will come back again. The main point is if your film is exposed to what you're taking an image for longer than the time scale it moves for, you see a blurred image. So to be able to make a movie, you need to have technical advances. At the time of the starting of photography, it was required to improve the film quality so that you could get a decent image without an 8-hour exposure. And additionally, it became necessary to have some way of shuttering, some way of controlling the duration of time that light was exposed to the film. So now there's two ways of achieving that goal. And for most of you who have a camera, that's done with a mechanical shutter. So in this case, the film is contained in a light-tight box, and then behind that lens you have a shutter. By opening and closing this shutter, you control the amount of time that light is exposed to that film and for how long that image is made. So what becomes critical is if you want to make a clear picture, if you want to have an instant photograph of a particular object as it moves, you need that shutter time to be faster than the duration that it moves. Alternatively, you can take your film and the subject that you photograph and contain both of them in a box that's not exposed to light. And now how you control exposure is by flashing the light source. This is like a strobe light at a disco. The dancers are in a dark room dancing to music, and as you flash that strobe light, you get a series of instant photographs of the dancers as they move. It is this method for making instant photographs that we'll use in our molecular movies. So now in the 1800s, when they were developing photography and the initial movies, there was an open scientific question and also a question of importance to the society, which was, what is the gait of a horse during gallop? The conventional wisdom at the time was when a horse galloped that it took flight temporarily, that during that gallop it had all 4 hooves off the ground simultaneously. Here's a painting from the 1700s by an English painter, but it was not limited to England that this conventional wisdom existed. Here's a painting from China with all 4 hooves off, again in the extended position. And here is one from the West of an American Indian riding on the back of a horse. Now, Leland Stanford, the founder of Stanford University and governor of California, in the 1870s decided that he was unsatisfied with the conventional wisdom, and he wanted a movie, scientific proof of what the gate actually was. So he hired a San Francisco photographer, Edward Muybridge, in 1872 to make such a movie. Now, before I show you that movie, I'd like to ask the audience, who thinks that the horse takes flight temporarily during gallop? For those who are willing to raise their hand, many. Now the second question, for those who think it takes flight during gallop, do you think all the hooves are off in the extended position, as the paintings previously showed? No. Well, you guys, you already know it all. All right. Here is one frame from that movie, and yes, you can see all four hooves are off the ground, and they occur simultaneously. When it's in the bent-legged position, here's that series of photographs taken, and let's try that one more time. And what you can see is that when it's closer to an extended position, it always has at least one hoof on the ground. Now, technologically, this required having a shutter speed of 1,000th of a second and collection of 10 frames per second. Movies continue to play an important role in science. So what I'm going to show you now is a movie that was collected just a couple of years ago of a drop of water splashing on a dry, smooth surface. The surprising thing that they found in this movie is how the water splashes depends on the atmospheric pressure it occurs in. At room temperature, when it lands, it splashes, but as you reduce the pressure, reduce it to a pressure similar to that seen at the top of Mount Everest, the way the spot splashes changes. So here's a movie. Unfortunately, it has a rather long lead-in telling you who did it. So here is room pressure, and here's the reduced pressure. And you can see up here, you see this large splash, but at the lower pressure, it just extends smoothly along the surface. Pretty exciting. So now this is a movie that was collected at roughly 50,000 frames per second. The only point I want to make is that a movie can actually tell you a tremendous amount. It can take something that maybe with some difficult differential equations to describe in mathematical sense this phenomena, a simple series of images can give you a very clear physical picture for the events that are occurring. But what we're interested in is making movies of molecules and taking photographs of molecules. Now this requires a very different sort of camera than the one that was used to take a picture of that water droplet. Now, as it turns out, a different series of technological advances was required to make the photographing of molecules possible. The first step of which was the discovery of X-rays by Wilhelm Röntgen in 1895. So what is shown here is one of the very first images taken with those X-rays, which is an image of his wife's hand. And what you can see here, like you would observe from a doctor's office, is that the flesh is rather transmitting. So you can preferentially see the bones and the ring on her hand. Not too long after that, with regard to taking pictures of molecules, Max von Laue found that if you take those same X-rays and now you shine them through a crystal, that the X-rays end up collecting in bright spots with a rather dark background. And it is this pattern of spots that can be analyzed and used to determine the structure of molecules, the distance between atoms and solids and crystals. So now what I would like to do is just give you a very brief sense of how that can be achieved. For that to be possible, you need to have a sense of what an X-ray is. So now an X-ray is a form of light, just like the visible light that's used to illuminate the screen here. And the difference between X-rays and visible light, or radio waves for that matter, is simply the wavelength of the light. Now out here at the radio wave, where the wavelength is extremely long, that wavelength duration can be on the length scale of a house. In the visible, that wavelength is smaller than the size of a cell, but not significantly so. And out here in X-rays, the wavelength is comparable to the distance between atoms and solids. And this similarity in the length scale of the wavelength and the distance between atoms is what gives that pattern of spots. And what that wavelength is on the order of an angstrom. That's that A here with the little hat on it. What is shown here is a chlorine molecule where the distance between the two atoms is 2 angstroms. Well, 2 angstroms, what's an angstrom? But then if you give the definition, it's still a big question. Well, what an angstrom is it's 1/10 billionth of a meter, which is about as easy to understand as what an angstrom was. So what I like to do is draw an analogy that hopefully gives you some sense of what that length scale is, or at least how small it is. So here's my analogy. The distance of a free throw in a basketball court, for those that don't play basketball, that's 15 feet. To this length in this molecule, this 2 angstroms, is the same as that free throw distance is to the distance between the Earth and the Sun. So now this free throw distance, it's pretty much the height of an adult. So what that means is when you think about how small you are compared to the distance from the Earth to the Sun, that's how comparatively small a molecule is to you. So now, as I mentioned, X-rays, the wavelength is the same. So that wavelength for the X-rays is also on the order of an angstrom. But how do you get that scattering pattern? And so what I have here is a little applet from online. So if you like it, you can come and look at it. You can go look at it on your computer at home. And what you have here is a light source and 2 slits. And what you see here is the pattern of light intensity that makes it through those 2 slits. So you see there's a bunch of vertical lines. Now the important thing about that pattern is that as I move the slits apart, the lines move closer together, and as I move them together, they move farther apart. So there is a relatively straightforward relationship between the distance of these slits and the pattern you observe. This pattern is very similar to that pattern you saw before from the X-rays. It takes some mathematical tricks to be able to convert this, but now imagine that instead of slits, you have 2 atoms, and instead of a visible green light source, you instead have X-rays. You're going to see a similar pattern there. And by knowing the wavelength of the light and the pattern, you can actually determine the structure. So that's how X-ray diffraction works. You see an interference pattern like these pretty ones here. With some mathematics, you can then turn it into an image of your molecule. So now this is actually, at the level of photography, a very well-developed and established technique. And in fact, what you see here is a photograph collected with X-ray diffraction of a protein molecule that was collected at SLAC here in the recent past. And this is a protein molecule that plays a critical role in the transfer of the genetic information in DNA into the proteins that do the lion's share of the work in your body. So this is the intermediary that helps translate that information from DNA into a functioning person. I chose this example because it was collected here, and this year Roger Kornberg and his colleagues who collected this data and created this image received the Nobel Prize in chemistry for the work. Yes? They're metallic centers. So these rings, these are termed alpha helices. They're the arrangement of the polypeptide chain. And then in this particular case, there are also heavy atoms associated with it. So the specific one here, I don't know. I believe that it's zinc, though. But before moving on, I think the important point I'd like to make is that this is an object that does work. It's not a static object, but the best we can do right now is take static pictures. The goal is to be able to watch this change, to do its job, to do that transformation, to create a series of images as it does that transformation. That's the idea of the molecular movie. That's the goal. So the question is, why can't we do it already? And the answer is, it comes back to the issue of exposure time. Those molecules, they just move extremely fast. So now the time scale that they move, to observe it, that X-ray, we're going to use that stroboscopic method. We need a flash of X-rays that's shorter than the time scale that they move. In this case, it's just not, we don't have the appropriately intense pulses of X-rays that are short enough in duration to make those images. They get blurry, just like the wings of this hummingbird. So how fast do they move? How short do we need those pulses to be? So to give you a sense of how fast they move, it's critical to keep in mind, as we just discussed, that molecules are in fact very small. So what we have up here, this is a macroscopic turbine from a hydroelectric power plant. Now it rotates, and it rotates about 10 times per second. A big object tends to move slow. Now if we take this and we shrink it down to the size of a protein. In this case, this protein is on the order of tens of nanometers. This is 100 times bigger than that angstrom that we just learned about. And now when it rotates in solution, when it's in water or in your body, it rotates about 100 million times per second. So certainly much faster. But now we're going to shrink the object we're looking at. We're going to go from a big molecule to a small one, a water molecule. And now we see that when it rotates about 100 billion times per second, 1,000 times faster. But in fact, it's not the rotation that we care most about when we think about chemistry. What we really want to know is about the vibrations of this molecule. So now our water molecule has one oxygen atom and two hydrogens attached to it. So now the vibration I want you to think about is one hydrogen, this hand here, and this is the oxygen, and they vibrate, they oscillate, they move closer and farther apart. This motion in a water molecule, because the atoms are very light, occurs 100 trillion times per second. Now it's this vibrational period that sets the time scale of chemistry. Now you can think about the breaking of a bond. So what's a bond? It's the attractive interaction between those two atoms. It's what sticks them together. It's the glue. Now if I want to break that glue, and it has a characteristic period, it's going to happen on the time scale of that vibration. So it's the vibrational period that sets the time scale of chemistry. So in the case of water, it's this 100 trillion oscillations per second. That time scale is 10 femtoseconds. So when I say femtosecond, just think in the back of your mind the time scale of a chemical bond. That's the key feature to keep in mind. So again, because this is so fast, sometimes analogies are useful. So now this motion of that molecule, that vibration, is to 1 minute what 1 minute is to the age of the Earth, the 40 billion-year-old Earth. So this is a really fast motion. That means that our X-ray pulses, if we want to make these instant images, need to only be on for this brief femtosecond period of time. So why do we actually want to make a molecular movie? And so like any movie, we need to be telling a story, and as it turns out, a chemical reaction has a lot in common with a story. Now a chemical reaction, it has a beginning. In the beginning, we refer to a term of reactants. Now when you think about reactants, it's kind of like the ingredients if you were going to bake a cake. These are your starting products, your flour and your butter. In this case, we have an atom here and a molecule. In the cartoon I've made here, this atom is going to form a chemical bond here, and this atom is going to break this chemical bond. So we start here. This is our beginning. Then, of course, we lead to the middle. Now, in a chemical reaction, the middle is this sort of awkward stage. It's kind of like the teen years for a molecule. It doesn't quite have this chemical bond. You know, it's not quite an adult, but yet it still hasn't lost its parents. So what we have here is a transient state. In fact, it's the imaging of these transient states that's so difficult and so critical to understanding chemistry. And then in the end, of course, we have our products, our baked cake. So as I mentioned again, what we want to be able to image is this shape here, this intermediate structure, which chemists have associated a term with, a transition state structure. So now, because a lot of these ideas are new, I'm going to give you a new cartoon that basically is giving you the same information. So this is take 2 on the same story. So now when you look at this blue line, think of it the way it looks. It's like a mountain with 2 valleys next to it. Now these valleys over here, we have a valley, and this is our reactants. And over here we have our products. And it's this hill in the middle. This is our transition state. So what makes this very difficult to observe is the life of our molecule here, or our reactants and our products, is a lot like the career of a sprinter. That's the analogy I'm going to draw now. Now, if you want to be a great sprinter, you're going to spend a lot of time training. And if you're going to be a reactant, you spend a lot of time just moving around without much occurring. It is only for a very brief time that you move up to this transition state and are transformed and end up as a product. So in short, so with the analogy of your sprinter, you train a lot. Hopefully you rest on your laurels a lot. Perhaps you wonder what might have been. But you only spend about 10 seconds running the race. So the ratio of the time scale, the time it takes to follow this path along this green arrow here, compared to the time spent looking pretty much like a reactant or pretty much like a product, can be on that ratio of many trillions to 1. So now think about a movie. Let's say you had a movie and you collected 10 trillion frames. What I'm saying is in all of those 10 trillion frames, only one of them is going to be what you were looking for. So, right, if you're lucky. So that means that'll never work. So what we need is a trick. We need a trick. We need a trigger to start the reaction. Now what our trigger is a short pulse of light. And this is actually what ties us back to the beginning, where I said that these movies that we make are very much relevant to solar energy research. So now what we're going to use is a brief pulse of light. This is a pulse of laser light. It's red here, so just imagine it's visible light. Now we're going to use that pulse to start a chemical reaction. Now this axis here is time, and it's also the direction that the pulse is moving. So this pulse moves to the side, it's absorbed by this water molecule here, and it dissociates this bond, out comes this atom, and as time increases, the atom moves away. If this pulse of light is short in time compared to how fast that atom moves, you can impulsively start this chemical reaction. So now we have a trigger. So you can think of this pulse here as a trigger, but we still don't know what's happened because we haven't been able to watch it. So now what we need to do is have a second pulse. We have one trigger pulse, and now we're going to have a second pulse, which in our movie is a pulse of X-ray, shown here in blue. And now what we're going to do is take a series of snapshots with our X-rays, where the variable of time is the distance between the pulse that triggers our reaction and then when we watch it. So here, that delay is very small. Let's say it's small compared to the time that it takes this atom to move. Now, when we have this trigger pulse occur and then we take an image, what we see won't look very different from what the X-rays would have seen if there were no trigger pulse. So this is sort of our initial starting point. Now we can increase that time between them, and now when the X-rays come in and they make an image, they generate a photograph, we see that the structure of the water molecule has changed. We then increase that time even more, and we see that it's moved even farther. So in this way, we create a series of photographs a series of instant pictures of the configuration of this water molecule, and that's our movie. Yes?
The X-ray pulse is full of more energetic photons than the trigger pulse. Won't it disturb the reaction?
It can, but if this pulse is so short, the effect that it has comes later. That's one issue. The other thing is while X-rays have very high energy, they also aren't absorbed very strongly. If they were strongly absorbed, you wouldn't see them on the other side of your sample. So with X-rays, you utilize the fact that it's weakly interacting. But yes, if this is intense enough and strongly absorbed enough, it will disturb this reaction. But you won't see it because that disturbance in time is happening out here, and you already took your image first. So now what I said up here is that we're going to borrow from the discotheque. So now, in this regard, the trigger here, our laser pulse, is like turning on the music. No music, no dancers. You turn on the music, and then you take a series of stroboscopic pictures, and then that's how you generate your movie. Now, our future, in this regard, is on the way, but it has yet to arrive. So we have an X-ray laser, but it's not here. Now before, unfortunately, to build that X-ray laser, the source we had before had to be removed. But we were able to do some initial experiments. And the difference between the experiments we did before and the ones we want to do in the future is our X-ray source was rather dim. It was a dull bulb compared to the X-ray laser we're going to have. As a consequence, we couldn't make movies of molecules, so we did what we could, and in that case, we studied the process of how a crystal melts. So we used these same ideas of starting a process with the laser pulse trigger, and then watching the transformation with a short pulse of X-ray light, but instead of watching a chemical reaction, we watched a crystal melt. So how is this experiment done? So just very generically, what you see is if you form a crystal, when the X-rays are transmitted through that crystal, all of the intensity gets collected in small spots, small bright spots, and then in between those spots, there isn't much X-ray intensity at all. Now you can contrast that to when instead of putting a crystal in your X-ray beam, you put a liquid. This is the scattering from liquid water. Here what you see is that all the scatter gets spread diffusely in rings and spread throughout all of space. That means that if you were sitting on one of these bright spots and you took that crystal and turned it into a liquid, you would see the intensity of X-rays drop significantly. So we're going to use that as our signature of the melting of our crystal. Now when we melt our crystal with our laser pulse, we destroy the crystal. So that means that we want to be able to measure a movie with just one X-ray pulse and one laser pulse. And so what I have here is a brief little movie describing that process. So here's our X-ray pulse over here. Now it's going to travel towards our crystal this way. And now we also have a laser pulse up there, and it's coming down like this. Now the critical aspect of this is that this laser pulse, because of the angle it's coming towards the crystal, it's going to hit this entire surface at the same time. This X-ray pulse, because it's coming at grazing incidence, is going to hit this surface at a different time at every point. That means at each point on the crystal, that time delay that we talked about before, that's the key time in our movie, is changing across the surface. So now, if we take the diffraction off of it and we measure an image, we're going to be able to see a time axis. So here's the animation. And what you can see is it moves across the surface, and as it does, the time delay changes. So now I'm going to back up. Over here on this side, the X-ray pulses arrived first. That means that even though the laser will eventually melt the crystal here, when the X-rays diffract off, they'll see a nice crystal because the X-rays got there first. In the middle, they'll arrive sequentially, and over on this side, the laser arrives first, melts the crystal before the X-rays come, and you don't see much X-ray diffraction. So that's the concept. And here it is, just stepwise again. On this side, the X-rays come first. In the middle, it's sequential. And on the right, you see that the laser came first. So this is an image from a single X-ray spot off that crystal. So now in the center of this image, the laser was focused. The other important thing to note is this color. As you go from red to blue, is just the number of X-rays detected. Or you could think of it as the height here. When the height is high, you have a nice, pure crystal. When you don't have much of a peak, that means you no longer have a crystal. So you can see that you transform from crystal to liquid within this image. It's not that the laser never hit here, it's that the laser hit here after the X-rays did. Now we can take that image and we can turn it into a single plot. Now what we have here, this is the number of X-rays detected. More X-rays means crystal. Here we have crystal. Less X-rays means we've started to melt. And now let's think about time. What does time mean on this axis? Well, this Fs means femtoseconds. So just think this is the time scale that atoms move. So on the time scales, so that means that we're losing our crystalline order on the time scale that atoms move. We're having a very fast crystal to liquid transformation. Where 0 here, that's when the X-ray and the laser arrived at the same time. So increasing time means you're waiting longer before you make a picture with your X-rays. In the context of the movies I was talking about, each one of these green triangles, in the end, we want to turn into a picture, a full image of that crystal. Right now, we have a triangle. But that's where we're moving to. To try and make it a little more comprehensible, perhaps, what we do is a little math magic. And instead of having number of X-rays over here, now we have the average distance those atoms have traveled. Again, 0 is when we start it. This is when our laser trigger happens. And what you can see is those atoms move more than an angstrom. Again, an angstrom is roughly the distance between atoms. So on a very fast time scale, they're moving angstrom distances. Yes?
How do you tell, the images overlap, and in the case of a diffraction X-ray picture, the spatial pattern of the diffracted beams matters. How do you sort that out?
I don't fully understand the question.
Okay, so say you got a crystal and causes 10 spots on the screen.
Oh, okay.
And you have a different crystal and causes 12 spots on the screen in a different pattern. You're not doing melting anymore, you're doing one crystal to a second crystal. And you've also got a spatial pattern in the fact that one X-ray beam comes in, the X-ray beam comes in at an angle, so different portions of the crystal surface give off the points from a different location.
Let's see. I think I can answer your question in part at least. The initial conditions are such that you only, for the way the X-rays come in and how the crystal is oriented to it, that you can only see a single X-ray peak. And our detector is small enough that the size of the detector is such that we only see that one diffraction peak. We'd have to rotate the crystal to see a different peak. Now, in principle, you could use a laser to change it, not to melt it, but to turn it into a different crystal so that the spots showed up somewhere else. But in this case, if you were to move that and see the same, you wouldn't see Bragg peaks anywhere. You wouldn't see these bright spots because, in fact, the laser is so intense it doesn't change what's the crystal structure. It makes a crystal and turns it into a liquid. There are no bright peaks anymore. Not only not on our detector, but nowhere in space.
Yeah, I get that, but I was thinking about what you're eventually going to use this for, where you wouldn't necessarily just want to melt to it.
I think we can address that maybe after the talk.
I certainly would be yes?
It sounds simple, but how quickly can we see this? Do we have to
I think that I'm going to back up to address that question. To here. The way we get time is by controlling the distance, the temporal distance between our trigger and the pulse we use to make an image. It's this is where our time comes from. Ah, I see. Yes, we need to slow it down. When we take it, we need to say have a slowing down factor of 10 trillion so that the images in a movie occur at a speed that your eye can watch them transform. Or in other words, when we have this picture here, each of these points, if we were to make a movie, you couldn't watch them on the time frame that they correspond to. They need to come, say, once every second, and then so that you take this very brief period of time and drag it out to a minute. Yes?
You wouldn't happen to know what the speed of these molecules are at this point in time? Is it on the order of speed of sound?
Yes. The answer is yes, it is similar to the speed of sound. That's actually that's a great segue to my next point.
I'll take the money later.
That was part of the deal? The important thing here is that the average distance traveled is increasing linearly. Now imagine you're in your car and you're driving down the highway. If your distance traveled is increasing linearly with time, that means you're moving at a constant velocity. So this means that our atoms are moving at a constant velocity, and if we look at this slope, it tells us what that velocity is. And the very interesting aspect of that is what this slope tells us is that while the laser has a very large effect, the velocity that those atoms move with is the velocity that they had before the laser ever arrived. They aren't made more energetic by the laser pulse on this very fast time scale. They just move apart. It's as if the bonds in the crystal, it's as if the laser came through and cut them all with a pair of scissors. So to make that point clear, I've made a little movie. So what we have here is my rendition of a crystal. So we have one atom, a spring, and imagine that this orange block here is all the other atoms in the crystal. This spring here functions as the chemical bond. It's the glue that attaches this atom to all the others. Now in a crystal, you can use fairly simple ideas for how they move, and as it turns out, they vibrate just like springs. So if you had a movie of the atom in a crystal in a short time frame, it would just oscillate, it'd go up and down, as my not so high-tech movie shows. So now the question is, how is that motion modified by the laser pulse? So now in this picture, as I just mentioned, I'm going to pretend that my laser pulse is like a pair of scissors. So when the scissors show up, that's the same thing as having our laser trigger happen. So what the laser pulse does is here we have our happy crystal moving along. In comes our laser pulse, cuts that bond, and what you see is the atom moves away at the velocity it had before it was cut. That is the full movie we have. Now in physics, we try to say that simple experiments and simple descriptions are powerful. So hopefully that's the case. That's state of the art, what you just saw there. Not the animation, mind you. But the near future, as I mentioned before, we're 2 years away from the commissioning of the world's first X-ray laser, which has been given the name LCLS. doesn't exactly roll off the tongue. But this is our exciting future. This is where we're going to be making our molecular movies and doing a lot of other exciting science as well that I assume will be discussed at this SLAC colloquium in the near future. And to close, I'd like to give you an overview here of SLAC. Here's our linear accelerator right there. This is 280 Sand Hill Road. Now you're here, right there in that building. Now over here at the Stanford Synchrotron Radiation Laboratory, that's where the photographs of that protein were made. So this is where we do our current state-of-the-art molecular photography. Over here near Stock Farm Road is where Muybridge made his movie of the horse. And right here, this is where in the not too distant future we're going to be making our molecular movies. Thank you for your attention.
Thank you very much, Kelly. I should point out that we have, of course, time for questions. I should also point out that after we are done with the questions, there will be cookies outside, and there will be also people which have those stickers. They're called Ask a Scientist. And feel free, please, to ask many questions afterwards. But please let's start out with some questions.
A few years back,
in the essence of, okay, so the question was, in 1999, Ahmed Zewail received the Nobel Prize for chemistry. And in the essence of why he received that was because he had used short pulse lasers to be able to make molecular movies. So in a talk, I left some of what has been done before out. So the short answer is that yes, people have been able to use lasers that are all in the visible light region to be able to watch chemical reactions occur in real time. But the kinds of systems that they can study are diatomic molecules in the gas phase. They're very simple chemical systems. Once the materials get more complicated, say, have a dozen atoms, or even if they're diatomic but now they're in solution, once you have a more complicated system, one that has more interesting chemistry, that has, say, industrial application, or is relevant to the chemistry in your body, you can no longer make those movies. You can no longer have a clear picture of the chemistry that's occurring. It's for that reason, for complicated systems, where you'd really like to be able to use an X-ray pulse, something that more directly sees structure. And so that's why being able to use an X-ray laser, a very bright source of X-rays, is so integral to moving beyond demonstration to actually being able to study chemistry that is more widely relevant.
I have a question. How long does it take from the time you take the snapshots of the, let's say, a protein, and the time it takes for you to analyze and find out what the configuration of the protein is?
I think there's enormous variation in terms of depending on it. I think my understanding is that now, for taking photographs of protein crystals, the most challenging part is making the crystals themselves. It's being able to make crystals of the most important and interesting biological molecules that is most limiting. Not to diminish the challenges of turning that, say, that crystal into a structure like that. It's just that a lot of that has been developed before. But I think in the end, data analysis is weeks to months.
Yeah, so on that red laser that was filming the crystal, was that carefully tuned so that the energy of the photon is equal to the binding energy of the atom in the crystal? So that's why the crystal just comes away because or is it just, I mean, is the laser somehow disrupting the bond? I'm not.
So, right. so what occurs, so what you excite with the laser are the electrons in the crystal. And it's those electrons that cause the attractive interactions between the atoms. It's the electrons that form the glue. Now, when you excite them with the laser, what you do is you change the way they're distributed in space. You change how their spatial distribution between the atoms. So you can move them from being in a configuration where they're like glue to turning them into a configuration where the atoms want to be repelled by each other.
So the reason why the atoms aren't excited by the laser is because most of the mass is in the nucleus, and it's only the electrons that are actually gaining energy from the laser. So.
Correct. Yes, the electrons are extremely hot, but the atoms haven't gotten hot yet.
Question way up there.
Earlier you showed a graph with 3 triangles relating the time in some kind of second to angstroms. It appeared to resemble a logarithmic equation. Is that accurate?
Can I answer your question in person? I'm not sure I understand, and I don't want to dismiss it, but I think that I think it's better for a one-on-one discussion. So when I'm done here, definitely come down and I'll try and answer it. Yes?
If you're interested in biological reactions, I understand.
Oh, I think well, yes, certainly.
The problem is that you have to crystallize the protein and presumably the reagents, and then normal biological reactions happen in an aqueous solution, not in a crystal. And how would that hang together? How would you actually get natural reactions to?
As it turns out, so one aspect of biology that makes making biological movies a challenge is most important biochemistry is not started by light. But there are some rather critical exceptions, like photosynthesis.
I assume you're aiming at photosynthesis because you made it to
Right. So in that case, or the way that you are able to see light with your eyes with rhodopsin, there are fundamental and important chemical reactions that are light initiated, and for many of them, they do in fact occur in the crystal. Whether they occur identical to how they occur under natural settings is debatable, but they do actually go through their photocycle. You can make a crystal of say, bacteriorhodopsin, and it goes through its full photocycle, and it's very similar to the proteins in your eye that you use to see. So yes, it does limit it, but there are important exceptions where studying biochemistry is possible.
Once you've created your pattern of the starting signal to the signal that actually takes the picture, and you've matched those up and you've got the timing and you're able to generate those with the speed you want, how do you actually capture the data that fast so that you have something to process when you're done?
As it turns out, the rate you have to capture the data is how frequently you get those sets of 2 pulses. You have a trigger, and then you have an X-ray probe, and then you have a bunch of dead time till the next trigger and the next X-ray probe comes.
But even then, the dead time is femtoseconds, right?
No, in this case, the dead time is milliseconds.
But then you're not taking
Yes.
taking moments in time that are actually following one another. It's like watching your dancers on the dance floor. They're over here, then they're over there, then they're over here. You're not actually getting a flow of time.
That's correct. So imagine it's the following. Now we're going to take the discotheque, and so we're going to play the same song over and over again. And each time so now what we're going to do is we're going to play that song, and we're going to take the first bar, and we're going to take one image. We're going to play to the end of the song. We're going to start it over again, and now on the second bar, we're going to take the second image. And then we're going to do it over again. That's the essence of how it's collected.
But you have to run the experiment over and over again.
That's correct.
That you're actually
Exactly.
That is exactly correct.
Wait up there. Excellent question.
Well, what that means is that for the particular example I gave, perhaps I chose poorly, we wouldn't be able to resolve the vibration of a water molecule. But that is one of the highest frequency, one of the shortest period vibrations possible, because what you're primarily moving is a hydrogen atom, which is very light, so it moves very fast. So there are some vibrations that with its initial configuration, we won't be able to image, but there are many we will. And one of the goals of the X-ray laser is to move from its initial pulse duration to shorter pulses. But there are many motions that we will be able to image when we start, just not the motion of the vibration of water.
So let's do 3 more questions. Please.
Kelly, I kind of lost track of the purpose of what you're showing the crystal. Is it this X-ray camera basically building meant to capture the crystal melting? Is that one of the things that you're going to try to accomplish?
That is one. The reason why we started there is it turns out it creates a rather large signal. So it makes the experiment easier. It was chosen primarily for experimental reasons. When we have an X-ray laser instead of a dim bulb, we'll be able to do a much wider range of science, because the number of X-rays in a pulse, there'll be a million times more.
So you're talking more crystal, like, for example, ice melting in the water?
We could watch ice melt, but we could also watch, ideally we should be able to, watch photosynthesis happen in a protein crystal. We should be able to watch a chemical reaction occur in a liquid solution. There are many, because we'll have many more X-rays, it'll make the range of science that we're able to do much wider. We won't be limited to systems that generate large signals.
Yes, so you say that you'll have to have the molecule do its performance again and again and again. If we're talking about something like photosynthesis, how can you make sure that that will happen again and again and again?
You have to illuminate a different part of the crystal each time, or say maybe only 10 times. In other words, the point is how often can you expect a material to go through that whole dance, come back to the beginning, and be willing to dance again? It depends very critically on what you're looking at. For some things, you can only watch once. It never goes back. So that means you have to have, in essence, you have to have a large collection of essentially identical samples. You could have a large crystal and a small beam, and you'd scan through the crystal. So you'd excite a fresh sample every time. If you had a liquid, it could flow. In other samples, they do repeat, so you can hit the same spot over and over again. But it is an issue.
And now the last question.
So it's really nice to be able to make movie in femtoseconds. So what kind of impact it can have on normal people's life? Like you will make them better medicine? Like you will make a bigger change in the physics law? So it's just like this nice picture of Sophie.
It is my hope that if we take a complicated chemical reaction, one that the current tools we have are unable to unambiguously determine the reaction mechanism. They're too complicated for our theoretical methods to predict the important attributes. That by having a better tool, a more clear picture of what happens, we can understand chemistry in general better. We could understand, ideally, once you're able to see that picture, now you can complete the cycle of making a measurement and thinking, how could you modify the molecule to change the chemistry? It's unclear. In that regard, it's exploratory. But there's also, because you're studying photon-initiated processes, it strikes me that it's likely to be relevant to issues of solar energy conversion and making new materials relevant to that. We'll see, though.
I think that's an excellent point to stop. It's like watching Martin Luther King in chemistry. Let us all go thank Kelly and then go up for some cookies.